All right, let's get right into it. Today, we're going on a journey deep into the actual source code of our universe. We're about to explore the bizarre, mind-bending, and truly fundamental rules of quantum reality.
I mean, think about it. It's one of the biggest questions you can possibly ask. Forget biology, forget chemistry for just a second. What are the absolute, rock-bottom rules that govern everything in existence? Well, it turns out quantum mechanics has the answer, and it's so much weirder and way more wonderful than you could ever imagine.
So, to really get our heads around all this, we're going to follow the story of a single quantum particle. And, the first step in any story is to understand your main character. But here's the thing. In the quantum world, a character's identity before you actually meet them is, well, it's a little fuzzy.
This is where we meet something called the wave function. You can think of it like a quantum character sheet. But unlike a character in a game that has these fixed stats, strength, intelligence, this sheet is pure potential. It doesn't say our particle is here or that it's moving at this specific speed. No, it says it could be in all these places with all these different speeds all at the same time. It holds every single possibility all wrapped up in this one elegant mathematical object. You see, a baseball has a definite position. A quantum particle, before we look, has only possibilities.
Okay, so we've got our particle just existing as this cloud of pure potential. Now, what happens when we want to interact with it, when we decide we want to actually measure something? Well, this is where the universe lays down some very, very strict rules about what we're allowed to find out. So the first rule is all about the kinds of questions you can even ask. In quantum mechanics, we call these questions observables. And think of it this way. You can't just walk up to a particle and ask, "Hey, how's it going?" You can only ask it very specific, measurable questions like, "Where are you?" or "How much energy do you have?" or "How fast are you moving right now?" These are the observables.
And here's where it gets really wild. For any question you ask, the universe has a pre-approved list of answers. These are called eigenvalues. So when you measure a particle's location, you won't find it just floating in some random spot. You will always find it locked into a specific state, like position A or position B, never in between. It seems the universe comes in these discrete, specific chunks.
Now, here's the crucial point. Even though we know all the possible answers we can get, we can never know for sure which one we're going to get before we look. This is called the Born rule. The best we can ever do is use that wave function to calculate the odds. It's like the universe is holding a loaded die. We can figure out the probability of rolling a 6, but we will never know the result until we actually make the roll. And that brings us to the climax of our particle's story. So we've got this cloud of potential. We know the questions we can ask, and we know the only possible answers we can get. And now we're going to make a measurement. We're going to look. And this single act is where all that potential finally collapses into a single, concrete reality. This is the famous collapse of the wave function. Before we measure, our particle is in what's called a superposition. And this is key. It really is in all possible places with all possible energies all at the same time. But the very instant we measure it, that entire cloud of possibility just vanishes. The particle is forced to pick one. It snaps into a single definite state.
Just let that sink in for a moment. The act of observation isn't a passive thing. It doesn't just reveal what was already there. No, in the quantum world, the very act of looking is what forces the universe to make a choice. It literally creates the reality that it measures.
And here's the crazy paradox in all of this. When we are not looking, that cloud of potential, that wave function, it evolves perfectly smoothly over time. Its behavior is described by the beautiful and totally deterministic Schrödinger equation. It's completely predictable. But the moment we look, all that beautiful predictability shatters into the pure randomness of measurement. It's this strange duality, predictable when you ignore it, but totally random when you observe it. So these rules, the wave function, the measurement, the collapse, they aren't just abstract ideas for a chalkboard. They have bizarre and profound consequences for how our entire universe is put together. Let's look at a couple of the most famous effects that pop right out of these rules.
One of the biggest consequences is the famous Heisenberg uncertainty principle. It turns out certain properties like position and momentum come in pairs, and the universe enforces a fundamental trade-off. The more precisely you measure a particle's position, the less you can possibly know about its momentum. It just becomes a total blur of possibilities. And, of course, the other way around is true too. You can simply never know both perfectly at the same time. These rules also give particles these distinct little personalities. Some particles, which we call fermions, like the electrons that make up pretty much all matter, are total loners. They absolutely refuse to be in the same state as each other, and this rule is actually why atoms have structure and why matter is stable. Then you have others called bosons, like photons, the particles of light. They are absolute crowd lovers. They love to clump together in the exact same state, which is precisely what makes things like lasers possible.
So there you have it. We've journeyed through the source code. A particle starts as pure potential, a wave function. We can only ask it certain questions and get certain answers, and we can only ever know the probability of each answer. The moment we ask, the particle collapses from all those possibilities into just one reality. And this leaves us with one final haunting question to ponder. If our observation is what creates reality, what is the universe doing when nobody is watching?